The concept of the universe being left-handed refers to the idea of chirality or handedness, particularly in the behavior of fundamental particles and forces. Chirality plays a significant role in the structure of the universe, most notably in the weak nuclear force, one of the four fundamental forces of nature. This force shows a distinct preference for left-handed particles, which has puzzled physicists for decades and contributed to some key discoveries in modern physics. Here's a breakdown of the major points to understand why the universe is considered left-handed. Chirality, from the Greek word for hand, refers to the property of an object or system that distinguishes it from its mirror image. Much like how your left and right hands are mirror images, but cannot be superimposed on each other, particles can exhibit similar behavior. A particle's chirality is essentially its handedness. A particle is left-handed if its spin, a quantum property, is opposite to the direction of its motion. A particle is right-handed if its spin is aligned with its direction of motion. For most particles, the laws of physics treat left and right-handed versions equally, meaning there is no preferred handedness. However, this symmetry is broken by one key force in the universe, the weak nuclear force. The weak nuclear force is responsible for processes like radioactive decay and neutrino interactions. Unlike other forces, like gravity or electromagnetism, the weak force behaves asymmetrically. It interacts only with left-handed particles and right-handed antiparticles. This preference was first discovered in the 1950s during experiments on particle decay and was one of the most surprising discoveries in physics at the time. This discovery means that in certain situations, such as beta decay, where a neutron decays into a proton, electron, and neutrino, the universe shows a preference for left-handed particles over right-handed ones. One of the most striking examples of this asymmetry is the behavior of neutrinos. Neutrinos are nearly massless particles that rarely interact with matter, making them extremely difficult to detect. In every experiment conducted so far, only left-handed neutrinos and right-handed antineutrinos have been observed. This exclusive chirality of neutrinos is one of the biggest unsolved mysteries in particle physics. Why should nature prefer left-handed neutrinos over right-handed ones? While no conclusive answer has emerged, one of the leading theories points to the early moments of the universe's formation, when this symmetry might have been broken. In 1956, Chinese-American physicists Tsung-Dao Lee and Chunning Yang proposed that the weak nuclear force does not conserve parity. The idea that the laws of physics should behave the same way if everything were mirrored, i.e., a universe flipped like in a mirror should behave the same as the original one. This idea was soon confirmed in experiments by Qian Wu, leading to a groundbreaking realization. Nature does not always mirror itself. In certain fundamental processes, such as those governed by the weak force, left-handed particles dominate. This breaking of symmetry is referred to as parity violation and is a unique characteristic of the weak force, unlike the other forces of nature that respect parity. The deeper question remains, why does the weak force prefer left-handed particles? There isn't yet a definitive answer, but several theories and hypotheses try to address this. A. Early universe and symmetry breaking. One possibility is that the preference for left-handedness arose during the early universe, moments after the Big Bang. During the period of cosmic inflation or phase transitions, a tiny asymmetry might have occurred, favoring left-handed over right-handed particles. As the universe expanded and cooled, this preference could have been frozen in, leading to the dominance of left-handed interactions we see today. B. Grand unified theories guts. Grand unified theories, which aim to unify all forces of nature into a single framework, predict that at high energies, such as during the early moments of the Big Bang, there was no distinction between the different forces. As the universe cooled, symmetry breaking occurred and the forces split apart, with the weak force showing its left-handed preference as a remnant of this phase transition. C. CP violation. Closely related to parity violation is CP violation, charge parity violation, where certain processes treat matter and antimatter differently. This phenomenon is important for explaining why there is more matter than antimatter in the universe. The relationship between CP violation and the left-handedness of the weak force is a topic of active research, with some physicists suggesting that these two effects might be deeply intertwined. The preference for left-handed particles in weak interactions has profound implications for the universe. It is a cornerstone of the standard model of particle physics, which describes the behavior of all known fundamental particles and forces, except gravity. The violation of parity symmetry by the weak force means that the universe itself is asymmetric in some fundamental way, which could hold the key to understanding why matter dominates over antimatter or why neutrinos behave as they do. Additionally, it has led to exciting developments in searching for new physics beyond the standard model. The discovery of right-handed neutrinos or evidence of parity restoration could reveal new forces or particles, potentially explaining the nature of dark matter or the unification of forces. The universe's left-handedness helps explain not only fundamental processes like particle decay, but also cosmic-scale questions, such as the imbalance between matter and antimatter. It is one of the clues that might help physicists bridge the gap between the known physics of the standard model and the mysteries of dark matter, dark energy, and gravity. In summary, the universe's left-handedness, observed through the weak nuclear force's asymmetric behavior, reveals a deep, underlying asymmetry in the fundamental laws of physics. This chirality breaks the mirror symmetry of nature and offers a tantalizing hint that the universe is more complex and possibly stranger than we currently understand. The search for why this happens is ongoing, and it holds the promise of uncovering new realms of physics.